It was like 2 minutes before my last class that anyone showed up. I was in there alone for a long time. Maybe this one's just at a more humane hour. Okay, so for a little bit of review, I mean, we didn't get very far, but we did talk about, you know, order of operations, so bed mass, and we just talked about, okay, combining like terms, which we're going to come back to today, so I'm not going to review it explicitly, but just as a reminder, we even talked about polynomials a little bit, and then just kind of solving problems by collecting like terms. And then we moved on to rational numbers, which are just fractions. And then we were going through the properties of these fractions. And we only got through 1 and 2, which is multiplying and dividing fractions, but we'll review those. In fact, I'm going to cheat and I'm going to bring this, this little blurb in. If you're writing these out, really the only thing that you need to copy out is just the property 1 through 6 and everything on the left-hand side. And then there's an example, and then it's got the description in words, of course, but as far as what you need, it's just the properties on the left-hand side. So in terms of review, what we'll do is we talked about order of operations, right, which is just bed mass. Hopefully everyone learned the acronym. I know there are different acronyms that do the same thing, but bed mass is the most common, so that's why I'm saying that. But if you had a different acronym that you used in high school, then let me know. But I guess you could, because the D and the M are interchangeable and the A and the S are interchangeable, I guess you could have BEMSA. Doesn't really, well, I mean, bed mass doesn't make sense either. We talked briefly about polynomials and collecting like terms to simplify. And then we also talked about multiplying and dividing fractions. Multiplying and dividing fractions. So what's kind of ridiculous is I didn't get a chance to pick up my notes, so I didn't teach this course last term. So usually I have kind of notes on the side, just to make sure that I'm, you know, saying everything that I want to say and staying on track. And then, but now I don't have my notes. So I have it's like iPad galore over here. I've got my notes on my iPad that I'm trying to follow, but it's very tiny. Anyways, good thing I can do chapter 1 in my sleep. So anyways, so we talked about multiplying and dividing fractions, and like I said, I'm going to cheat and just bring in these properties of these fractions. So that would be property 1 and 2. Remember, so for just quick review, right, to multiply, you can just multiply across. There's nothing that you need to remember, right? And it can even be more than 2 fractions, right? You could have 3, 4 fractions, and as long as you're multiplying, you can just squish them all onto 1 fraction. If you're dividing fractions, so if you've got a fraction over a fraction, and remember I showed you, I always do this, right? I always have a fraction over a fraction, and then to kind of help myself visualize the flip and multiply, I take my denominator fraction and I flip it and I multiply, right? So I just kind of tack on whatever values are in the fraction and then I flip and multiply. So kind of so the first one, just this is still a review, to multiply fractions we just multiply across. Oops. Whereas to divide fractions, we flip and multiply, right? Once you're back to multiplying, it's easy. You can just smush things across. But if you've got something like, well, maybe let's use real numbers instead of these variables. So if you've got something like 4 over 5 divided by 6 over 3, for example, right? Then the first thing you have to do is put the 4 and the 5, 6 over 3, and then you're going to flip that denominator and then multiply. So here, this gets flipped. So this becomes 4 over 5 times 3 over 6, right? So you flip this, oops. I'm not doing this very clearly, am I? Good thing I feel like I did it properly last day. So you have to flip and multiply. Okay. And then once you're multiplying, well, 4 times 3, we know it's 12. And 5 times 6, it's 30. And you can probably, it simplifies, I'm just going to leave it alone, right? And what we're going to try to get in the habit of is just writing these in exact form, which means not the decimal approximation. If we go to our fancy calculator here, 12 over 30. Oh, right. So I've got 12 divided by 30 is 0.4. Here, this one doesn't actually give me, so as soon as it gives me a decimal, then I just want to keep it as 12 over 30, right? The decimal is an approximation, and the 12 over 30 is an exact answer. Might be easier to think about 0.4. But here, what I'll make a note of, this is our exact answer. Right? Versus 0.4 is the approximate answer. As soon as you have some sort of decimal, in this case, it terminates, right? 0.4. So we can use 0.4, but it's still considered approximate. All right, so that's kind of the, oops, that's not a very good end of review symbol. There, that's the end of our review. Okay. Just until we know what all these things are. So if you're dividing fractions, then you have to flip and multiply. If you're adding fractions, we have to have a common denominator. Okay, so in order to add or subtract fractions.
Professor?
Oops, sorry.
I have a question.
Sure.
In the above one, like you said, like we do have to write the decimal ones. So if there is like 30 divided by 15, then we can simply divide it, like it the answer will be 2. So then we can do it that way.
Yeah, you're allowed to do that because it's a whole number. You can do that. Even here, I wouldn't be upset about 0.4, but if you did kind of 2 over 3, for example, then you would want to leave it as 2 over 3. So this was kind of a bad example.
Okay.
But because it terminates, it's safe.
Okay.
But if it keeps going, like 2 over 3, for example, then you would want to definitely keep it as 2 over 3.
Okay. So like if we know like there would be a lot of calculations, then we should leave it like this only.
That's right.
Okay. Thank you.
Awesome. So in order to add or subtract fractions, we need to have a common denominator, right? A common denominator just says the denominator has to be the same. So we need to have a common denominator. Okay. So if we keep going through these properties here, property 3 says a over c plus b over c is a plus b over c. Notice that we've got this common denominator. So I'm just going to write that one out here. Property 3 says a over c plus b over c is a plus b over c. Notice the common denominator. C. Okay. So here, if you're adding fractions or subtracting, it doesn't matter. It would work the same. A minus b, so a over c minus b over c would be a minus b over c. So what you want to do, as soon as you see adding or subtracting fractions, you want to say stop, okay, and make sure that you have a common denominator. If you don't, you need to force it, right? If you do not have a common denominator, you need to force it. Okay, so what I mean by that is, and here's kind of a side note. I do it in a not so elegant way. The reason I do that is because it works every time, right? And so you don't need to get fancy with the math. And so how I'm going to introduce it is slightly different from the textbook because, of course, the textbook does it the fancy way with the lowest common denominator. I'm not going to do that. But I'll always use the same method and it'll always work. And so that's what we're going to do. Okay, so what we do is if you see that you, that you don't have the common denominator, right? What you're going to do is you're going to force it by multiplying those denominators, and that will be your common denominator. So to force it, you multiply all the denominators together. So there could be more than two, right? All the denominators together and use that as the common denominator. Okay, so that's what property 4 is telling us here. So notice here in property 4, you've got a over b plus c over d. Notice that b and d are not the same, right? So what I'm going to do is I'm going to say, okay, my common denominator is going to be b times d. Okay, so let's just pause and write that down. And then we'll talk about how that came about. And this is going to be so important for the rest of the course, that if at any point, it's not making sense, and this is something that people struggle with for a long time. So don't feel bad if it's not making sense, but just work at it until it does, okay? Because it's going to be so important to understand. So property 4 says if you have a over b plus c over d, right here, not common. Okay. So what I'm going to do is I'm going to use b times d as the common denominator. Use b times d as the common denominator. Now, I know because I'm in math and I, have done this for a long time. For me, using the variables is the clearest way to do things. But I know when you're not really used to working with variables, then it's not very useful. So we'll do it with the variables because that's the proper way, but then we'll do a numerical example as well. So don't worry. But the idea stays the same. So if I'm going to have b times d as the common denominator, then what I need to do here is I need to multiply by d. And what I need to do here is I need to multiply by b, as in Bob. Hard when all these letters sound the same. Or sound similar, rather. So what I need to do is I need to multiply the first fraction by d, but the hiccup is I can't just multiply by d down here, right? Because that's going to change what this thing means, right? But what I do is I multiply by 1. And so that's a really common thing. And I can't remember if I've brought it up already because it's so common. Multiplying by 1, right? And so here, in order to force the common denominator, we will multiply each term, and maybe I should say each fraction, just to be clear. Each fraction by a convenient value of 1. Right? Such as d over d is 1, right? Or b over b is also 1, right? So remember, you don't want to alter, oh, whoops, there. You don't want to alter the meaning of this thing, right? But if you multiply by 1, right, a over b times 1, it doesn't change anything, right? So 4 times 1 is still 4, 3 times 1 is still 3, right? And so we're allowed to do that, but we just pick convenient values of 1. So, and then we do the same thing for c over d. So what I need to do is I need to figure out, okay, well here on this first term, I need to get a d. So here I'm going to multiply by d over d. And over here, I'm going to multiply by b over b. Okay? And so what this looks like is I'm going to have a over b plus c over d becomes a over b times, and I'm just going to use a completely different color just to emphasize, times d over d, which is 1, right? To create the common denominator, which was bd. Right? That's what we decided it would be. So now I move on to the next term, plus c over d, and then again times a convenient value of 1, which in this case, I have a d, but I'm missing a b, so now I have to do times b over b. Okay. All right, so now I'm multiplying fractions, so I do those individually, right? And let's see here. We're back to multiplying fractions here. So you're going to do those individually, zip them up, and then we can add them because then we'll have a common denominator. So this becomes multiplying fractions. You can just multiply straight across, right? So you've got AD over BD plus CB over DB. Multiplication doesn't matter, right? 1 times 2 is the same as 2 times 1. So you can reverse this order so it looks the same, or you can just recognize that this is the same term. Right? Now I'm back to that situation where I have a common denominator, right? Now they are the same. Now I'm allowed to combine the numerators. So I add the numerators and put them over this common denominator, and that's from property 3. So this becomes AD plus CB over BD. Okay. So let's do an example, right? And same thing goes for subtraction again. I'll keep switching to my eraser. There we go. So for example, if we have 15 over 22 plus 1 over 2, you can do fancy things like multiply by 11 to make this 22, right? A lot of the time, I definitely don't see those quick moves, right? And so what I just did, so like I said, my way is it'll always work, but it's not the most elegant way, right? So here you can look at this and say, oh, well, if I multiply this second fraction by 11 over 11, then I would have a common denominator of 22. I don't like to waste my time kind of seeing if I can find some fancy common denominator. So what I'm going to do is I'm just going to use a common denominator of 2 times 22, so 44. So I'm going to force this common denominator of 44. Okay. So these are not the same. Use 22 times 2, which is 44, right? But it's a little bit easier if you look at it as 22 times 2, because that means you're going to multiply this first fraction by 2 over 2 and this second fraction by 22 over 2, right? As the common denominator. Yeah. Right? So I've got 15 over 22 plus 1 over 2, which is going to be the same, right? And so I've got this equal sign, so that means I can't change the meaning of it, but that's going to be the same as 15 over 22 times a convenient value of 1. 2 over 2 in this case, right? If I want 22 times 2 as my common denominator, then I'm missing the 2, so I have to do 2 over 2. Whereas here, plus 1/2, so 1 over 2 times, and now if I want a common denominator of 2 times 22, well, I have the 2 component, so I need to get the 22, so times 22 over 22. Multiplying by 1 does not change the equation, right? So that's good. So now I'm multiplying across, multiplying fractions, zip those up before you go ahead and add them, right? So 15 times 2 is 30 divided by 22 times 2, which is 44, plus 1 times 22 is 22 over 44. Notice that 22 over 44 is still 1/2, right, if you reduce it. And of course, 15 over 22 is the same as 30 over 44. Because that's the whole game, right? We're not changing anything. All right, so now I have this common denominator, so now I can combine these, right? And I combine these by adding the numerators over the common denominator. So this becomes 52 over 44. Good. So I want to show you guys, I made it a little bit cryptic, I guess, in hindsight. Go to our Moodle page here. So what I did was I posted kind of general math review. And of course, this is from my different course that I'm also teaching, but I thought it might be useful. So definitely it just goes through some properties of real numbers. So how does multiplication and things, how do they work? How do negatives work? And then here are the fractions. And then notice that there's these kind of practice problems, extra practice problems that you can work through. And I also posted the solutions. So make sure that you're able to go through and do these problems without a hitch. So those are on our Moodle page. They're completely optional, but if you want to make sure that it's all solid, then that's a good place to start. Okay. So that was property 4. Spent some time there, huh? Okay. Property 5 says that, okay, if you have AC over BC, so meaning you're able to pull out a common factor of C. Now, I want to just kind of, I'll mention this, and then we're talking about factoring later on today. So it might be a good intro, but here you can only cancel numbers if they're multiples in both the numerator and the denominator, right? And so here, property number 5, now I can't remember what it is. AC over BC, too easy. AC over BC, right, is the same as C times A, just rewriting, just to clarify that I've got this common factor here of C. So I can extract that to the outside over C times B, right? We have a common, we use the word common a lot, don't we? Common is common. A common factor of C, right? C over C is just going to cancel, and that becomes a 1. So 1 times A over B is 1 times A over B. Oops. Which is just A over B. So all this is saying is we can only cancel a number or a variable, if it is a common factor in the numerator and denominator. Numerator and denominator. Okay. So like I said, we'll come back to factoring, but basically you're just pulling out multiples, right? The one that I do want to get to is this last property, which is really useful. If you have a fraction a over b is set equal to c over d, then what you can do is you can rewrite this as a times d, which is equal to b times c, and I'll show you how that came about. But you're just cross multiplying. But we're going to use this a lot if we're talking about solving for x, for example, right? So property 6. If a over b is equal to c over d, cross multiply to eliminate fractions. So what that says is that, okay, if you just think about how, solving equations works, well, if you wanted to move this b from the denominator over here to the right-hand side of the equation, right, then you would have to multiply both sides by b because it's being divided on this side. So you end up doing the opposite of what's happening. So here you'd have to multiply by b, but from that previous property, right, those b's are going to cancel. So you have a is equal to c b over d. And then I want you to do the same thing, right? To move this d over to this side, technically what you're doing is you're multiplying by d. D over d goes to 1. So times d. When I multiply by d, the whole idea is to move it over, so it should disappear. It just becomes 1. D over d is 1, right? And so what we have is we have AD is equal to CB. Okay. Cross multiplying is very useful if you're dealing with solving for x. So for example, let's see here. Solve for x. So we've got something like 45 over 21 is equal to x over 77. Right? Here, kind of a baby problem, right? But as soon as we see that, okay, well, I can just cross multiply, right? I can multiply things over here, multiply this 21 over to the right-hand side, then I'll be able to shake out that x, right? And so you just want to try to, so if you're solving for x, you want to try to get it on its own, of course. So first thing I'm going to do is I'm going to multiply this 77 over to the left-hand side. And usually what I do is I just end up skipping this step where I show that I'm multiplying both sides by d, and I just do it over here. And that's totally fine if that's where you want to go, because that's what I do. 45 over 21, and then I'll just say times 77 is equal to x. Now, I've solved this, right? But I want to clean this up a little bit, right? And so I can do 45 over 21 on my calculator and then times it by 77. Or if I want to play it safe, then remember that 77, you can rewrite as a fraction, right? 77 over 1. So here, we can always write a number as a fraction by putting it over 1. Okay, so that's another thing that we use quite a bit is, oh, I can just, now it's obvious to me that I'm multiplying fractions, right? 45 times 77 over 21 times 1. Now 45 times 77, I have no clue. Maybe later. Pro version. Not yet. What was it? 45 times 77. 3,465. All right. Hello. Doesn't want to. There. Now I've forgotten what it was. 3,465. Oh, great. QuickBooks. Hey, at least it's useful. Never used it, but I run the risk of forgetting that number again. 3,465 divided by 21 is equal to X. And I'm not going to try to simplify this. I'm just going to leave it as 3,465 over 21, and that is our X. Well, now that I glance at my notes, maybe I should try it. 3,465 over 21. Let's go to our calculator. I don't want that. Divided by 21, it works out to a whole number. So that's why I should try. I should always try to see if it becomes a whole number, but in this case it did. 165. So X is equal to 165. And here, Rupert, one of my kind of quirks, well, it's not that weird, is that I like to have whatever I'm solving for on the left-hand side. So here, in kind of one go, I'm going to rewrite this. So I think we can all convince ourselves that 3,465 over 21 is equal to X is the same thing as saying X is equal to 3,465 over 21. Now, it's not always going to be that obvious, and there will be times when you go, hey, how did you just get there? Because I'll often do two things in this move. So I move this X over here, and I move this 165 over here. I'm just getting you used to my my quirks. All right. So those are all the properties of fractions that we need to be really, really good at working with. Definitely adding and subtracting fractions and finding that common denominator is going to be so important. Okay. So, any questions before we keep going with the next section, which we're going to talk about expanding and factoring. So we already talked a little bit about factoring, but I want to talk some more about expanding and factoring expressions. I'll keep an eye on the chat. So if something comes up, then feel free to throw it in the chat, but or turn your mic on. Totally fine. I get startled though. So, all right, I'm going to start this on a fresh page here. So section 1.4 is on expanding and factoring. Okay. So in those notes that I conveniently posted from my other course, but that kind of apply to you guys too, or definitely do apply. Expanding is essentially when you remove brackets and make something as large as possible. Is removing brackets and making an expression as large as possible. Right, kind of large. Okay. So for example, if you have A times B plus C, and I know you guys don't typically like variables, but here, this is the easiest way to see it. Expanding this expression would mean, okay, I'm going to multiply this A inside, right? Because this A multiplies the B as well as the C. So here, this becomes AB plus AC. Okay. Just as an example, if you have 4 times A plus 3, and I ask you to expand this, right? Or maybe you want to solve for A, right? In order to solve for A, you have to get it out of these brackets. So then the natural next step would be to expand these to remove the brackets. So then you have 4 times A plus 4 times 3. 4 times A. And now notice that these brackets aren't actually doing anything. I just like to have them on there to indicate that I'm multiplying, because sometimes it's not obvious, as in the next term when I do 4 times 3. Okay, so I keep the brackets, but these brackets aren't doing anything. Unlike here, where the brackets around A plus 3 were showing me that, hey, 4 is times each of these terms, right? Here, I've only got A inside and 3 inside, so now it's just multiplication. Right, so here, I use brackets, oops. To indicate multiplication. Okay. So now I can get rid of those brackets. 4A plus 12. Okay. It's my experience that expanding is usually no problem, right? We're usually okay with expanding. It's the factoring that is a little bit tricky. So factoring is essentially expanding moving backwards. All right, so factoring is expanding in reverse, essentially, right? So where we pull out common factors or common multiples and put them outside brackets, typically. We pull out common multiples and put them outside brackets. To the first assignment, well, we didn't really get very far last day, so that's why I haven't made an assignment, but I'll probably postpone the first assignment. It'll be due next week sometime. I'll give you a week to do it. We'll see how far we get today, and we'll probably be able to do an assignment just to kind of see where we're at after today. So I'll post one today, and then you'll have a week. So we'll do Tuesday. How about? Yeah, same with quizzes. I keep forgetting that we're doing quizzes here. We'll probably, I have to see how the quizzes are laid out. So we'll hold off on the quizzes until we've covered a little bit more material. How about that? I feel like we haven't done anything. We've done a lot, but I need more. You guys are on top of things. Me, I'm like, let's wait. Let's wait. But I'll get those put together. Good. Okay, so Factoring is essentially expanding, but in reverse. And so you pull out common multiples and then you put them outside brackets, and it's usually just to condense an expression. To condense an expression. Right? And there can be other reasons you're factoring to cancel, for example. But let's see here. For example, if you have, let's do 16 plus 2a, right? If you have to factor this thing, right? Well, there's no a that I could pull out here. So what I'm going to do is I'm going to focus on this 2. So what I want to do is I want to try to rewrite 16 as a multiple of 2, which I can do. So what this ends up looking like is 2 times 8, right? Just rewriting 16 as if it's 2 times 8 plus 2 times a, just to emphasize that I've got this 2 on the outside. Now I'm going to pull those out. Okay. So this becomes 2 times, and then when I'm pulling that 2 outside, I have to have the 8 plus a inside the brackets here. Okay. One thing to be careful about, so here, this is the factored expression, and you can always double check your factoring by expanding it again and make sure that you get back to the same expression that you started with. So we can always expand after factoring to make sure we arrive back at the same expression or at the original expression. To make sure we arrive back at the original expression, right? So 2 times a plus, 8 plus a is 16 plus 2a. So it checks out. Okay. All right. So you've got 16 plus 2a, good. One thing to kind of be careful about, if you have a multiple of 1, right? And so beware of a situation like, well, let's keep it simple, 2 plus 2a. Okay. So what you're doing is you're still extracting that common multiple of 2, right? 2 times, and moving a little bit faster here, but what I need to be aware of is that this is going to be 2 times 1, right? So you have to have this 1 plus a. Okay. So we need to keep that multiple of 1. Need to keep the multiple of 1. Right? In order to be able to expand this back, if you had forgotten, okay, I can pull out a common 2 and then 2 times a, well, that's just 2a, right? And so in order to keep this structure 2 plus 2a, you have to have that multiple of 1. Okay, so just be aware of that because it happens. So for example, what if we have to factor p times, or sorry, that's the factored, plus PRT. This is going to come up later once we get into interest problems, right? But here I'm seeing a common multiple of P, and I've got that exact situation here. Common multiple of P. So this becomes P times, and here I've got that situation, right, where I've got 1 plus RT. You always want to make sure that you can expand it back to the original. And you can just kind of check P times 1 is P, good, plus P times RT, which is exactly what we have. Good. Okay. How about another example? This is 21 from the textbook, although I guess it could change, so those numbers don't really make sense. So what if I have to factor something like 3b plus ab plus 1 plus t in brackets times b? Okay. Just some terminology. Each lump here is called a term, okay? And so I've got a common factor of b in each term. And there is a common factor of b, so combine that, of b in each term. Okay. So what I can do is just being really careful, right? Pulling that common b outside and wrapping everything else up in brackets. Okay. I have, and I'm just going to rewrite what I have here. So 3b plus ab, shifting it way over to the left because I'll need room on my right-hand side, plus 1 plus t times b. Now, one thing I want to kind of make note of is you could absolutely expand this b inside, right? This would be b plus tb. I'm not going to do that because that would be working against my factoring, right? Because then I'd expand it, but it's allowed, right? There's no harm in doing that. But here I'm saving myself a step by just treating this 1 plus t as if it's one thing, right? Because I've already got that common multiple of b outside. So this becomes b times, and then I just want to go through and list all the things that b is a multiple of. So 3 plus a plus, and I'm going to keep 1 plus t in brackets just to emphasize that it's one thing. Okay. So now I can expand this here, right? And I can eliminate these brackets because they're not actually doing anything, right? Brackets only do something if you're multiplying or dividing something on the outside. So we've got b times 3 plus a plus 1 plus t, which I can simplify, right? 3 plus 1, if I collect like terms, I get 4 plus a plus t. So this becomes b times 4 plus a plus t, and then I'm all simplified. Right. One thing that I'll definitely want to do, especially when I'm dealing with something kind of large like this, right? I'll want to expand this out and just make sure that I arrive at the original equation here. So expand to make sure my factoring was good, so here I've got just kind of on the other side, right? So now I'm going to practice expanding as well. So b times 4 plus a plus t is 4b, and this is kind of a pretty common thing. So even though b is on the left-hand side here, you could definitely write b times 4, that's fine. But typically we put the variable on the right-hand side. There are very few instances where I'm not going to put the variable on the right-hand side. So this is pretty common, right? So if you switch these around, that's good. Even alphabetical order if you want, and then plus BT. Look at how inconsistent I am, right? But so, all right. Or maybe I am consistent, right? Alphabetical in the sense that a numeral is always kind of before the alphabet. And keep going. Hey, I am consistent. This does not look exactly like what we started with, right? Sometimes we need to do a little bit of massaging to get it there, right? This does not look like 3b plus ab plus 1 plus t times b yet, right? But what I'm going to do is, like I said, if you wanted to, you could have expanded this right away, right? And once we expand it, then it's going to look the same, right? So you should always be able to kind of massage things until they look the same. So if we do 3b plus ab plus 1 plus t times b, well, that's going to be 3b plus ab plus b plus bt. And if I collect like terms, I have 3b plus 1b, and then ab is another term and bt is another term. So I have 4b plus ab plus bt, which now they're the same. Hey, that doesn't look like a smiley face. Looks like kind of a scared face. There. Okay. So far we've been expanding and factoring pretty simple things. What if we have to deal with something like, so that's the end of our example here. What if we have to expand something like a plus b times c plus d? Okay. You have two options. They do the same thing, and to me, they're hardly even discernible, right? So I can't really tell the difference between the two. But we have two options. We have two options for solving this, or sorry, for expanding this, I should say. For expanding this, okay. The first option is to have something like a plus b times c plus d. You can treat this as one thing. Treat this as one thing and expand as before. Wait. Little slip here, so I twist in my chair. So you can treat this as one thing. So then you've got a plus b And then you can expand that times C plus A times, or A plus B times D, right? So what that looks like is, I'll just rewrite it here, is A plus B times C plus D becomes A plus B as one thing times C plus A plus B times D, right? So you treat that as one thing and then you expand it. But then, of course, we're going to need to expand again, right? And so what I should do is I should write a follow-up here, then expand again. Right? So now here, I can expand this C into A plus B and this D on A plus B. So what I end up with here is I get AC plus BC plus AD plus BD. Right? Once you expand all that out, that's what you end up with. Right? And you can scan this to make sure that you don't have any common terms, right? Or like terms, I should say. So I've got A times C, there's no other A times C term. There's a B times C, there's no other B times C term. A times D, same thing, B times D. They're all unique terms, and so I'm done, right? The other option that you have is FOIL. First, outside, inside, last. FOIL itself doesn't really make sense, but this is how I do my expansions. So whether you call it FOIL or just expanding is up to you. But FOIL is kind of typically how it's summarized, I guess. So I use this, but I just call it expanding instead of FOIL. But now that I've said that, I'll probably end up calling it foiling. But it doesn't matter. FOIL is just supposed to help you. So first, outside, inside, last. It doesn't really make sense to me. Never has, never will. Because I'm dead set on it, I guess. But we've got the same situation, right? So here, we're just trying to expand this. So I'm showing you two ways of expanding this. And so if you know how to do it, then you know how to do it already. Don't worry about it. Okay, so to expand this, what we do is I'm going to take this A, right? So each term in the first kind of block, I'm going to multiply by each term in the second block, right? And then I'm going to move on to the second term, and I'm going to multiply by each term in the second block as well. So this looks like A times C, that's my first move. A times D, that's my second move. B times C is my third move. And finally, B times D is my fourth move. Okay. So this is supposed to be first, outside, inside, last. I don't know. So here, oops. First, outside, what color did I use? Green. Inside, last. Foil. So what this looks like, right, is A times C is AC plus A times D is AD plus B times C plus B times D. Oops, I did it in the wrong order. There. Notice that besides the order of these terms changing, right, we end up at the same thing, right? AC and BC kind of moved a term, right? AD is in here too, and BD. Notice both methods arrive at the same answer, which would be really bad if they didn't. So both methods arrive at the same answer. Okay. So let's do a couple of examples here. If I ask you to expand and simplify, and I want you to expand and simplify x plus y, and then times 3x plus y. So working with those variables is super common, so we're just going to stick to the variables. Otherwise, things condense to just a number, which is kind of boring, but so that's why we're going to be working with these variables. So what I need to do is, like I said, I use this method where I just kind of go from the x times 3x plus x times y plus y times 3x plus y times y, right? So you just work through them methodically. And when you're done with this first term in the first block, then you move on to the second term, expand it out. So this becomes x times 3x. Now, when we're first starting, I'm going to write things out in the same order. As we move along, though, I'm going to rewrite this as x times 3x squared, right? I'm just going to morph that x in there. Okay, x times x is x squared. So eventually we'll just kind of start to simplify this as we go. But for right now, I just want to illustrate that each term is hanging around. So plus x times y plus y times 3x plus y times y. Okay. So this becomes 3x squared, 3x to the power of 2, plus xy plus 3xy, because I like to have that kind of same order, because now I see that I'll be able to combine these, and then plus y squared. And of course, this is just where we're beginning. So if it's feeling like a bit much, then don't worry, we're going to do a lot of practice, and it's going to get better. So here, right, I've got an x to the power of 2 term, a y to the power of 2, but I've also got x and y here. So here, these are like terms. So this becomes 3x squared plus, and then just to show it, or sorry, I don't know why I did plus y, xy plus 3xy. I'm going to put in brackets to show that I can zip those up, plus y squared which is 3x squared plus 4xy plus y squared. And then I'm simplified. Okay. We're going to come back to exponents, but because we haven't introduced exponents, right, how did we move from x times 3x to 3x squared, and same thing with y times y as y squared? Just as a note, in general, x to the power of a plus x to the power of b, you can rewrite as x, oh, sorry, I don't know why I did adding, times, that's what we're doing. I'm just gonna scoot these closer together then. Cheating. So x to the power of a times x to the power of b. I don't know why I said adding. It's x to the power of a plus b. Right here we have the same base, which is going to be used there. And then to combine those exponents, we add them. Right? So what we've done is x times 3x is really x to the power of 1. And maybe I should move that 3 outside. 3 times x to the power of 1 times x to the power of 1, which is 3 times x to the 1 plus 1, 3 times x squared. So here, right, just did a little side note, and also on the y squared, I guess. And we'll come back to exponent laws, but for now, that's all we need to know. Okay. Uh-oh. I've done it again, haven't I? I always forget to give you guys a break. Okay. Let's do one more example, because that'll be the end of section 1.4, and then, or two more examples rather. But let's do one more example, and then we'll take a break, and then we'll head into section 1.5. So we'll do one more example. 4. I know I'm trying to be better about giving you guys breaks. I always forget. I just blah, 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 blah. How boring for you. Exhausting rather. Maybe not boring, but exhausting. So if I want you to expand and simplify. Now, here's a doozy. Make sure you give yourself lots of space on the right-hand side, so kind of smush it up on the left-hand side. So x minus 2 times 2x squared minus 3x minus 4. Okay, so here, keep your wits about you, right? You've got x minus 2. So you've got options, right? You can treat x minus 2 as one thing and just multiply it in on each of these 3 terms, right? We've only seen 2 so far, but it behaves the same way. Or you can work methodically and say x times each of these terms, and then negative 2 times each of these terms, and then sum them all up. It doesn't matter how you do it, but like I said, I like to just take x times 2x squared, x times negative 3x, x times negative 4, negative 2 times 2x squared, negative 2 times negative 3x, negative 2 times negative 4, and then add all those up. So no matter how you slice it and dice it, let's see if we can work through this problem. So I encourage you to work through it on your own alongside here, and just make sure that you end up at in the same place. So I've got, this becomes equals x times 2x squared plus x times negative 3x plus x times negative 4. Okay, so I'm gonna run out of room here, just as a kind of a math notation thing. If you're kind of running over a line, what you should do is indent from the equal sign and just put your next plus sign here, And then so you constantly indent just to make sure that you can see that it keeps going, right? So it's going to look like this, plus -2 times 2x squared. Notice that I'm keeping this -2 in brackets and I'm still adding, right? That's because I don't want any trouble. But if you wanted to, you could just use -2 times 2x squared. That's totally fine. But I just want to highlight that these are on their own. Plus, and then -2 times -3x plus -2 times -4. Okay.
Professor,
Yes.
how did you got the x minus 4? Because there was no x in the equation with 4.
So that's going, oops, that's going from, from here, x times -4.
Mm,
So it goes like this. That's the first term, x times 2x squared here.
okay, sorry, I missed the whole equation. My
There you
screens were over there.
go. No worries. Good. Glad we could clear that up. All right, so now I'm going to expand this out in an effort to simplify, right? So eventually I'm going to end up looking for like terms. So what I get is I get 2x to the power of 3 by that exponent law that we just discussed, right? If I have x as my base, x to the power of 1 times x to the power of 2, I can combine to make x to the power of 3. So 2x to the power of 3 minus 3x squared minus 4x, right? Just kind of rearranging and multiplying a little bit. Minus 4x squared. Here, I'm going to try to keep it on one line here. Give myself a little bit more room. Sometimes I write too lofty. There. So minus 4x squared plus -2 times -3 is positive 6. 6x. -2 times -4 is plus 8. Okay. So now collect like terms to simplify. Okay. So what I'm going to do is I'm going to look for the combinations of variables that are the same. So x to the power of 3, I'm looking for other x to the powers of 3. I don't see any, so I can write that down on its own. This becomes 2x to the power of 3. And then I've got -3x squared. So I've got an x squared. So now I'm scanning for other x squared. And I do have one. So I'm going to pull those together. So I'm going to collect those. -3x squared minus 4x squared. And often what I'll do is as I go through and I transfer things down, right? If I'm pulling things together, I'll often cross these out. I don't want to do that this time, but once we get into bigger things, I'll often just cross things out as I move them, just to keep track. Then I move on to my x's. I've got -4x plus 6x. So I'll write those together. And then plus 8 is the only constant because there's no variable. Okay, so I collect these like terms. Okay, so I've got, remember we just look at the coefficient. So -3 minus 4 puts me at -7. And then -4 plus 6 puts me at +2. So where I'm at here is I have 2x to the power of 3 minus 7x squared plus 2x plus 8. Okay. Technically, what we did here is we factored out a common x squared, so x squared, and then times -3 minus 4, and that's how we got to this -7, right? But if you want to think about it just as combining these coefficients, it's fine too. All right, nice. Okay, so let's take just a break until 11:20, 11:30. And then we'll be fresh. Wait, that's 8 minutes. I don't know. You guys don't get much of a break. How about 11:25? Oops, not 2 else. That's meant for the 11. How weird is that? 5-minute break. Anyways. So let's keep going. Time flies when you're having fun, right? So let's just do another example. It's kind of a big example. So I'm going to start it on a fresh page here. So just as an example, if I want you to simplify something weird like 3y divided by 1 plus 0.06 times 175 over 365. That's weird, right? That's weird looking. There. Okay. So we've seen kind of big fractions like this before last day, right? And so what you're going to do is you're going to simplify the numerator and the denominator independently of each other, right? And then it's not until the very end that you can simplify and maybe cancel some terms. So here 3y is pretty simplified. So I'm going to focus my attention on simplifying this denominator. And of course, BEDMAS applies. So what I have is I've got division, and then I'm multiplying, and then I'm adding it to 1. So it's important that you first do this section, right? This multiplying and dividing BEDMAS, right? So you do your division first here, then your multiplication, right? Or in the order that they appear. It actually doesn't matter if they're being smushed together. So this is going to be 3y divided by 1 plus, and I'm going to keep this 0.06 times, and I'm going to use brackets instead of this multiplier, only because I find when I use x's or kind of the times, they end up looking like x's, and that can be really confusing. So I'm going to use brackets instead. And what I want to do is I want to do 175 over 365. And on my calculator, here we go. Clear 175 over 365. Okay, it's this big nasty number, but remember, I want to keep all those decimal places, even the ones that aren't being shown. So remember how we stored stuff last day? So I'm going to store this. There's the STO button here, store, and I'm going to use it in slot number 1. So you get STO1, so store it in 1. Oh, I think maybe I held it too long. Recall 1, no. What was it? It was 175 over 365. I managed to hold the store button for too long. Store in 1. And now I can recall 1, and it should bring up that same number. So I'm going to make a note in my work. Let's see here. Uh, 0.47, and then I'll do ... to indicate that it keeps going, right? And for now, later I won't use different colors, but I just want to highlight that I stored it, right? And so you should show me, and also to remind yourself where you stored stuff, right? Just show me that you know to keep all those decimal places. That's really important, right? And so I do it in two ways, with the dot, 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 as well as telling you where I stored it. More for me to remember. So now I can do this number times 0.06. So what I end up with is 3y over 1 plus, okay, here we go. Oh, find the song stuck in your head.
What's that song?
Maybe I should get the ad-free one. Although it makes for a nice, nice little break. So if I do recall 1 and then times that by 0.06, okay, I get this 0.028 dot, 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 which I'm going to store in 2. Just picking anywhere you want to store it. And remember, you could store in 1, but then you lose what you stored in 1 earlier. So at least for each problem, I like to store in different values. Oops. So this becomes 0.028 dot, 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 and I'll just write in a different color to highlight here. That's in store 2. Okay. Once I add this to 1, right? So now to simplify here, I do 1 plus 0.028, but recall 2, right? To make sure that I keep all those decimal places. So this becomes 3y divided by 1.028 dot, dot, dot. And I'm going to store this in 3. So I'm going to go back there, because I've got this 0.028 blah, 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 plus 1. I'm going to store that in 3. Okay. So now, because I have 3y divided by that 1.028 blah, 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 I want to do 3 divided by recall 3 equals, okay, 2.91611851. Okay. So here, come on, turn. I know it's showing up normal for you guys. There we go. So this becomes, right, if I want to simplify this, I can pull this 3 over 1 point, well, recall 3 times y. So what I get is I get 3 over 1.028 dot, 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 which is in store 3, just as a reminder, times y. Right, I can pull that y outside, and then I can simplify this in the last step. So this becomes, and I'll use the squiggly equals approximately equal to, because I'm going to have to stop after the digits that aren't displayed anymore. So this becomes 2.916111. Of course, I have it on the side here, 851 times y. But let's just check it in our calculator here. 2.916111851. We understand that it keeps going beyond that, but that's as much as we're able to show. Okay, so okay, here you don't want to do any rounding, because what's likely happening is this 2.91 blah, 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 blah is going to get multiplied by some dollar amount. So you want to keep all those decimal places and ideally save them for your next calculation. Here, we're just ending here, but just kind of keep all these. Keep as many decimals as you can. Okay. Good. So, done a lot of kind of BEDMAS and fractions, and we even talked about exponents briefly, but we'll come back to that, like I said. But for now, I'm going to go on a fresh page because we're ready to head into section 1.5. 1.5 is really fun because we're just solving systems of equations. And so once I show you how to do it, we'll kind of get in the groove. So solving systems of equations. So a system of equations is really just, well, in the end, it's two straight lines and you want to find the point of intersection. So we will be given the equations, and we're going to stick to two, the equations for two lines, for two straight lines. And we want to find the point of intersection. And solving the system means finding the point of intersection. Right. That's as far as we'll go in this course. You can incorporate more than two variables. So, but for now, or for us, we're just going to keep it to two variables. So a system of equations, oops, a system of equations looks like this. Something like 4x plus 2y equals 8, and 2x minus y is equal to 7. Okay. So each of these are straight lines, right? Straight lines because we have just an x and a y, right? And you can rewrite this as y equals mx plus b, which you might remember is just the general equation of a straight line. So you've got the slope times x and then the y-intercept. So you can rearrange by solving for y, you can rearrange these into straight lines. So as long as there's an x and a y, then you've got a straight line. Now, here, right, we've got our x's and our y's. We have two unknowns, x and y. Unknowns. Okay. Two equations, two unknowns. So if you have to solve for two unknowns, you're going to need two equations. In order to solve for two unknowns, unknownness, we need at least two equations, but we need two equations. Three unknowns. You would need three equations, right? So you need as many equations as you have unknowns. Okay. Like I said, we're just going to stick to two, but just to be aware that that's the general setup. So as many equations you have, you need, or as many unknowns as you have, that many equations you need. Okay. So what we need to do, and there are a couple of ways that we can kind of rework this thing. So here we've got this system, right? And in order to solve this system, right? And solving the system means finding the point of intersection, right? It means finding the point where they have the same x and y values. Okay, so solving the system means finding the point of intersection. No harm in repeating myself. Means finding the point of intersection which means the x values and the y values, the x values and y values will be the same. Okay. So just to illustrate, right, if you've got this kind of grid here and you've got your first line, right, and then you've got your second line here, then this is the point of intersection. Okay. And that point of intersection is going to map down to some value of x and map over to some value of y, right? X, y. This is where there is, where we've solved the system. Okay. So if two lines are parallel, right, it means they're running alongside each other, they'll never have an intersection, right? And so it's possible that you might never have a point of intersection, and we'll see what that looks like. It's also possible that the two lines are on top of each other, meaning every point is a point of intersection, right? And so there are a couple of different things, but for now, hey, I'll be back for office hours. Just talking about the little reminder that came down in case you missed it. So there are a couple of different kind of special case scenarios that we might come across, but for now we're just going to find the point of intersection. And to do that, if we have a system like this, 4x plus 2y equals 8 and 2x minus y equals 7, there are a couple of things that we can do here. We're going to use one equation inside the other. So what I like to do, and there are a couple of ways that we can do this, but what I like to do is I like to solve for one of these variables, and I scan the system to figure out which one is easiest to solve for, right? So to solve the system, we will solve for one of the variables in one of the equations, pick the easiest one. Okay. Then substitute it into the other equation. Then substitute it into the other equation. You don't want to substitute it back into itself because that's not going to get you anywhere. But then substitute it into the other equation and solve for the remaining variable. Okay. for example. And so what I do is it's often useful to number the equations. It is often, I'll say helpful, maybe not useful, helpful to number the equations. So if we've got our system, let me go back to our system here. 4x plus 2y equals 8 and 2x minus y equals 7. Okay. What I'm going to do is I'm going to number this equation 1 and equation 2. And then for my steps, right, what I'm going to do is I'm going to kind of scan this thing and see what's going to be easiest to solve for. It's pretty easy to solve for y, but then I have to deal with this pesky negative, which I don't want to do. So looking here, right, I could solve for x, but then I have to divide by 2. That's not really clean. But what I will do is I'm going to solve for y in equation 1. That seems to be the easiest thing for me to do. Solve for y in equation 1. So I have 4x, so here's equation 1, 4x plus 2y equals 8. So 2y is 8 minus 4x, be careful. And then y is 8 minus 4x divided by 2. Remember, to cancel this 2, it's one of those properties we talked about. I need to extract a common multiple of 2 here, which I can do. So here I need to factor out a 2. 2 times 4 minus 2x divided by 2. So that's going to go away. So then I have y equals 4 minus 2x. Y equals 4 minus 2x. Now, and I'll kind of leave it for us to come back to next day, but now what I'm going to do, so this was from equation 1, right? Y equals 4 minus 2x. So now what I'm going to do is I'm going to substitute y equals 4 minus 2x into the other equation, which is equation 2. So I get 2x minus y, but in this format now. So y is going to be replaced by 4 minus 2x. So 2x minus 4 minus 2x with that negative in the brackets. Then, just to give you an idea, you're going to be able to solve for x. Once you have the x, you can come back here and substitute it in here and solve for y. But like I said, we'll do that next day. Any questions? I'll stop this here.